Hello, pre-calc students. This is Mr. Beck. Today we're going to be talking about the graphs of sine and cosine. We've been talking about sine and cosine as ratios, and ratios end up being the x and the y values on the unit circle. More specifically, if we're looking at sine of x is the y over r ratio, or the coordinate, the y coordinate on the unit circle. Now, in the past, what we've done is we've looked at all of these individual ratios and we've calculated the ratios based off of the specific angles that lead to those ratios. Now, what we're going to do is we're going to put them together in context and look at the sine ratio as an actual function itself. So if you look at the sine ratios as a function, the first thing that I did was I had all of my fractions converted to decimals so that we can have a relationship there. And then we're going to plot those decimals. So we're going to plot pi over 6 comma 1/2, which is right here. Pi over 4 comma the square root of 2 over 2, which as a decimal is about right there. And if we continue around, what we will see is that the sine graph will actually, or the sine function will produce a wave. And this is called a sinusoidal wave because it's a sine function. So sinusoidal waves are important because everything involving light travels in waves, sound travels in waves. The transmission from cell phones travel in waves. So understanding how these waves travel and interact with each other is what we're going to end up looking for. So I'm going to try to put a lot of these waves in context, and as we do manipulations of these equations, we're going to state what the context of what the transformation is on it in real life. One of the big things that I do want to look at is when we're talking about a unit circle. Any angle, you can take the sine of any angle, just because if you remember on a circle, you can either go forward and keep going, or go backward, keep going. So you can continue to make any positive or any negative angle, which is why the domain of the sine function is all real numbers. The range of the sine function, because it is the y over r ratio, or the y value on the unit circle, the highest y value that we have is 1. The lowest y value we have is -1. We can see that on this graph for a range from -1 to 1. Sine is an odd function. The way we looked at it is the positive angle theta, and I'm probably going to go ahead and change that. The positive angle theta yields a certain y value, where the negative angle yields the opposite y value. And because it's the opposite y value, what ends up happening is f of negative theta is equivalent to negative f of theta. Now we're looking at this in terms of a function, and we can see that sine has symmetry over the origin. And that symmetry over the origin is what we consider odd functions. Then we have amplitude. Definition of amplitude is going to be the distance between the peak and what we're going to call the equilibrium. So the equilibrium is going to be what that sine wave travels over, or it's the distance from the trough to that equilibrium. So this distance right here is going to be my amplitude, and this distance right here is also my amplitude. When it comes to that amplitude for a sine function, the amplitude is 1. And then the period is 2 pi, and the reason why the period is 2 pi, let's draw a circle one more time. The reason why the period is 2 pi is as we travel around the circle, the y values start at 0, go to 1, go to 0, go to -1, and go to 0. It's at that point, after we've gone the full circle, that the y values will begin repeating each other. So that's what we call the period, also known as how long before it repeats. I do like, we do have a visual of this on GeoGebra. So let me go ahead and click on GeoGebra, open this up. And what I like about the GeoGebra app, or the GeoGebra app here, is this shows you that the y value on the circle, on the unit circle, translates into the sine value, and that's what creates the sine wave. Whereas cosine, now when it comes to cosine is the horizontal distance. So the horizontal distance that we see like the blue arrow that you see there, translates to the blue arrow as a vertical distance. And so the cosine function looks like that, which should make sense because the cosine of 0 is 1, cosine of pi over 2 is 0, cosine of pi is -1, cosine of 3 pi over 2 is 0, cosine of 2 pi is 1. So the cosine looks similar to the sine graph, but the cosine actually starts at the peak and then travels through the sine wave accordingly. So going back to this screen, when we take a look at the cosine graph, as I mentioned, the cosine graph looks very, very similar, but the cosine graph starts at the peak, and then we'll end at the peak, and it'll go peak, equilibrium point, trough, equilibrium point, peak, or peak. And so that's the way that I'm going to refer to doing the graphing. When it comes to the graphing, all these waves are going to look very similar to each other, which is kind of the downside because we lose sight of what's really going on if we just draw a bunch of the waves that look exactly the same. So that's why I want to talk about the different characteristics and what happened. I guess just to finish up with cosine, once again, the domain's all real numbers because any angle, and keep in mind that the x-axis represents angles, so any angle can go in and the y value represents the ratio. And all of these ratios will come out. And those ratios are from -1 to 1 also. Cosine is an even function. The way that we looked at it before is if we had an angle theta and an angle negative theta, that the x value here is the same as the x value here. They're both positive in this case. Therefore, the cosine of negative x, or the cosine of negative theta, is equivalent to the cosine of theta. And that is exactly what even functions do. The period is also 2 pi because the x values don't repeat until after you've gone all the way from peak to peak. And the amplitude of this one is also 1. So what we see here are, we see the key points that we're going to be looking at in terms of sine. And as I sort of started mentioning, for sine, we're going to take a look first at what's the equilibrium. And I'm going to really consider that like the 0, because as a sine wave, you go in a positive direction, you go in a negative direction. I'm going to consider that the 0, which if there's no shift, it is 0. So I will say our sine points are 0, peak, 0, trough, 0. So that sine pattern then is going to repeat itself. But we'll be looking at this as this is a positive sine function, and we'll talk about negative sine functions too as we get to that. If you notice that peak and the zeros all occur at the quadrantal angles, which is why we want to look at those quadrantal angles to help us come up with the where the peaks and where the zeros are. Cosine, these are going to be our key points. Cosine of 0 is 1, and then all of our quadrantal angles end up yielding these points. So we're going to say cosine is going to go from peak to 0 to trough to 0 to peak. So let's begin the graphing of things that aren't just a basic sine or cosine. And the way we're going to do this is first identify what the equilibrium is. So the equilibrium is really going to be our vertical shift, which we're not there yet. So we're going to talk about these functions first, which just have a vertical dilation. If you remember when we were in chapter 2, we had y equals a times f of x. So that is a vertical dilation. The vertical dilation here ends up being, or ends up changing the graph, that it changes the amplitude, which if it changes the amplitude, it's going to change the range of the graph as well. Now, in context of real life, the amplitude is going to change. I want you to think about these waves, and you can see the waves down there. I want you to think about these waves as sound waves. If you're very, very quiet, the amplitude of a sound wave is very, very small. Or if you're very, very loud, the amplitude then gets much, much bigger. So that vertical dilation is going to be the amplitude, or it affects the sound, or the, I want to say the strength of the wave, if you will. So moving right along, if we have a vertical dilation only, then what happens is we will take a look at this. We are going to first, again, identify the equilibrium. That's what I started out with. Our equilibrium is 0 because right now I'm not changing that. So my equilibrium is y equals 0. The second thing I'm going to look for is where does this wave start and where does this wave end? Now, for this wave to start and where this wave ends, right now, for a while, we're going to keep our period at 2 pi. So we're going to start at x equals 0, and we are going to end at x equals 2 pi. And then the sine graph goes 0, peak, 0, trough, 0. And we're going to put that into 4 equal parts. So after, and what you see here, after we find the start and the end, we are going to put it into 4 equal parts that model the quadrantal angles. And then we follow whether this is a sine graph or a cosine graph. So that's why we went 0, peak, trough, or 0, peak, 0, trough, 0. Now, remember, the domain is all real numbers. So what you see in blue is what I call the principal wave. So this is the principal wave, because this is the one that we are generating based off of the equation and based off what we know about sine of x, which you can call it a parent function. So the principal wave is in blue, and then I extended that principal wave on in green. One of the things I don't like is I don't like having arrows on here, because arrows represent, the moment I put like an arrow on here, represents it's going to go down forever. So I don't like having arrows on there. Sometimes some people do, but that's up to them. I'm okay with that. So this graph does extend forever, and since it extends forever, the domain is from negative infinity to positive infinity. The range, I told you the range was going to be changed because that amplitude, which the amplitude, I think I skipped over that. The amplitude is the magnitude of that a value. So the magnitude of that a value is 3. So our range goes from our bottom case of -3 to our top case of +3. So remember, just talking through this, and this is really like talking through it in a lot more detail than we probably need to for a graph as easy as this. First thing we look for is that equilibrium. Second thing we look for is where do we begin, where do we end? And then we break it up into 4 equal parts. In this case, we have 4 boxes between those 2 points. And then we say this is a positive sine graph, so 0, peak, 0, trough, 0. Moving right along, and we're going to do this one a little bit more efficiently. Again, the first thing we're going to look for is the equilibrium. And the equilibrium, we can tell there's nothing added on here, so the equilibrium is going to be y equals 0. Then we figure out our beginning. Now, we don't know what affects the period yet, so the period is still 2 pi. So our beginning, it goes from 0 to 2 pi. The sine graph, let's break it up into 4 equal parts, which is nice and easy because there are 4 boxes between those 2 values. This is a positive sine graph, so we have to know where the peak is, and that peak is 5 halves up. So our peak is 5 halves up, and our trough is 5 halves down. So our sine wave is going to go 0, peak, 0, trough, 0 along all those pieces. And then we extend it on. And we extend it on because the domain's all reals. We just talked about what the range was. The amplitude is 5 halves as well. For our third graph, one more time, there is no vertical shift. So since there's no vertical shift, it's y equals 0. This time we have a negative sine graph, but I think I'm jumping ahead of myself. We begin at 0, we end at 2 pi because our period is still going to be 2 pi. We don't know what changes that yet, but it's still 2 pi. Our amplitude is 2, and our amplitude we find by taking the magnitude of that number. So the highest value we're going to go to is 2, the lowest value we're going to go to is -2. And this is a negative sine graph, so this is the very first time that we're experiencing a negative sine graph. And if you remember, that negative causes a reflection over the x-axis. So it's a reflection over the x-axis, which is what you see below. I actually like to think about this right from the beginning is, what happens if we make a t-chart and our x value is pi over 2? Then we have to take -2 times the sine of pi over 2. So that would be -2 times the sine of pi over 2, which is 1. So the y value should be -2, which is why our graph goes from 0 to trough to 0 to peak 0. And yes, we could look at it as a reflection over the x-axis, but let's not forget that numerical aspect of the triforce. So then extended, of course, and our domain's all reals. We talked about the range and the amplitude go together. Now we have cosine graphs. Cosine graphs. Well, just like before, we're going to figure out what is our equilibrium, and there is no change here to the equilibrium. So with the equilibrium still at 0, then we're going to say, okay, our beginning, I'm jumping ahead of myself, our beginning is 0, our end is 2 pi because our period is still going to be 2 pi. Then our peak is going to be at y equals 2. Our trough will be y equals -2. And as a cosine graph, this is our first cosine graph. We go from peak to 0 to trough to 0 to peak. And then we continue extending it. So what's in blue one more time is going to be our principal wave. So the principal wave of the cosine will look like that. And continue it on. For E, E is a negative cosine graph. So again, there's no vertical shift. Therefore, y equals 0 is going to be our equilibrium. The magnitude is going to be 3, or the amplitude is 3. So we're going to go from -3 to 3 as we look at our range. Kind of draw that in, if you will. Now, as a negative cosine graph, as I mentioned a moment ago, the negative cosine graph, well, where it would be a normal peak to 0 to trough to 0 to peak, it's now reflected. So it's a trough to 0 to peak to 0 to trough. And then we create the cosine graph. Ooh, very badly highlighted right there. And as usual, extend it on because the domain's all real numbers. Graph the same thing. We're going to go from, it's a negative cosine graph, not shifted. So, and there is no change in the period. We still don't know what causes that yet, so we're going to keep it at 2 pi. So it's a negative cosine graph, so we go from trough to 0 to peak to 0 to trough, and then extend that graph on. Moving along. Now, when it comes to what I have in problem number 4, I would want my students to be able to take a look at the equation and be able to have a very quick visual of those graphs, which is why I went into a lot more detail on those than a lot of students think that I really needed to, but that's because I wanted you to see how those graphs are created. I wanted you to visualize. More importantly, when I look at this is a negative cosine graph, so I'm expecting trough to 0 to peak to 0 to trough. What is our domain? All real numbers, because it's a cosine function. Range would go from -8 to 8 because there is no vertical shifting. Your period is still 2 pi because we haven't seen anything that's changing that yet. Our amplitude is 8. On part B, this is a positive sine graph, so it should go 0, peak, 0, trough, 0. Now our domain is all reals because it's a sine function, and then again our period's 2 pi. Now this one's a little bit different, that this one screws up people a little bit because I put a 2 pi on the outside. What that means is my amplitude is 2 pi, and from my equilibrium, which is still 0, I go down 2 pi and up 2 pi. So there's a lot of 2 pi's involved in that. Well, let me just leave it at that. There are a lot of 2 pi's involved in that. So moving right along, same thing sort of happens here, but this is a negative sine graph, so I'm expecting students can say 0, trough, 0, peak, 0 because of the negative sine graph. The amplitude is pi over 4 because it's the absolute value of our A. Period still 2 pi. But because our amplitude is pi over 4, we drop down pi over 4 and we go up pi over 4. And that's what creates those points right there. And domain's all real numbers. So moving right along, let's finally establish something slightly different. And this means we're going to have a vertical shift. So if we have a sine of x plus k or a cosine of x plus k, what that k does is it creates a vertical shift. A lot of times you are going to write it as k plus a sine of x, just so we can distinguish between sine of x plus k versus sine of x plus k. Now, all the problems that we have really are going to be in this form right now. We're going to do those later. But if you don't see parentheses, you know that it really represents the sign ends right there. So addition, subtraction, break apart, what happens after the sign. So we have a vertical shift. That k creates a vertical shift, and the reason why it's a vertical shift is because this really models f of x plus k, like y equals f of x plus k that we did way back in chapter 2 last semester. So we have a vertical shift. So as I look at part A, that plus 3 means I have a vertical shift of 3. And then this is 2 cosine of x. So our period's still going to be 2 pi. So our beginning is 0, our ending is 2 pi. This is a positive cosine graph. Positive cosine graphs go from peak to 0 to trough to 0 to peak. And then we extend that on. Our amplitude is 2. It's the absolute value of 2. Our range is now going to be affected. So from our equilibrium of 3, in essence, we're going to go 3 up 2 and then 3 down 2. So that's why our range goes from 1 to 5. So if you really, really wanted to, you could create a formula for this. You could say our range is always going to go from k minus the magnitude and then k plus the magnitude, or amplitude, we can call it that too. So k minus the amplitude, k plus the amplitude. If you wanted to, I don't like to necessarily focus on that as a formula as much as there's the idea. If you can mentally create that, you're in much better shape than memorizing it. So for part B, that 2 means that we are going to have a shift up 2. This 4 means our amplitude is 4, but most importantly, this is a negative cosine graph. As a negative cosine graph, again, period 0 or 2 pi. So we start from 0, we end at 2 pi. As a negative cosine graph, we go trough 0, peak 0, trough. And then we extend the graph on. So range is -2 to 6, which you could look at as 2 minus 4 to 2 plus 4. Our domain's all real numbers. Like domain of everything is going to be all real numbers for sine and cosine. Now for C, we do have a negative sine graph shifted up 3. So y equals 3 is going to be our vertical shift, our equilibrium. And then as a negative, our period's 2 pi. So we're going to begin at 0. We're going to end at 2 pi. And then we go from 0 to trough to 0 to peak to 0, according to our amplitude of 3/2. So our range goes from 3/2 to 9/2. Domain is all real numbers. Then we get to a phase shift. When it comes to a phase shift, if you think about it in terms of sound waves, a phase shift would be kind of like a delay in when that sound is going to occur. So it's really going to be shifting the entire wave over horizontally. So that horizontal phase shift, what it does is it really is going to affect the start and the end. This is going to be the first thing that's going to affect the start and the end. Right now, the period of everything is still going to be 2 pi because we have not affected the period yet. So we have not seen what does. We're just kind of building all the different pieces up to it. So our horizontal shift, also known as our phase shift, when we take a look at this, we could say, okay, this is a shift. And if we think function mentality, f of x plus 2 is a shift left 2. So if we have the x minus 2 inside the cosine, then that means that we have a shift right pi over 2. So what that means is our equilibrium 0, first thing we always look for. We start at pi over 2 to the right, and then when we add 2 pi, so if we add 2 pi, so plus 2 pi, then that's going to take us to 5 pi over 2 over here. And I probably shouldn't have put that right there. But anyway, now if we look at it as a positive cosine graph, it goes peak 0, trough 0, peak. Now that's going to be the fast approach to graphing these. If you can do that for all the problems, I would strongly encourage you to do that. Now, are you going to be able to do that for all the problems? Maybe yes, maybe no. It's really depending on your personal level and your personal ability. So if you are able to do, or if you aren't able to do this, then I do have a backup plan. My backup plan is to set what's inside. In this case, I'm highlighting again the x minus pi over 2 at the top. We're going to set what's inside, bad plan on my part, set what's inside equal to 0 because that's your normal beginning, and set it equal to 2 pi because that's your normal end. What that does is that's your algebraic approach to figuring out what your beginning and your end is. So again, you set what's inside. So what's inside equal to 0 and to 2 pi because that's our beginning and our end. So let's take a look at it with this graph. When it comes to this graph, I do see that it is a shift left pi over 3. But what I do is if I say x plus pi over 3 equals 0, then I get x equals negative pi over 3, which is going to be my beginning. If I set x plus pi over 3 equal to 2 pi, I get 5 pi over 3, which is going to be my end. Now, vertical shift is 2 units up. And now I have my beginning and I have my end. One of the things that I sort of skipped over is how do we accurately put this on the graph that we're given? So if we accurately put this on the graph that we're given, and we're trying to go from negative pi over 3 to 5 pi over 3, I would encourage each unit to just be pi over 3. So then we have 1 pi over 3, 2 pi over 3, 3 pi over 3, which is pi, 4 pi over 3, 5 pi over 3, and so on. So that way we can establish what our beginning and what our end is. Then this is going to be our first case where how many boxes are in between because it's no longer 4. That shift left pi over 3 now sort of messes with us because we can't put this on the scale like we normally do. So by understanding how I can build my x-axis, what I'm going to do is I'm going to establish that I'm going pi over 3 each time. This does leave me with 6 boxes in between. And in a normal year where I do this a little bit more numerically, we're kind of crunched for time this year, so we're going to just count boxes. So halfway through those 6 boxes is where we're going to have, in this case, since it's a positive cosine, we go from peak to trough there, and then we're going to go back up to peak. Then if we go halfway through that, that's where we're going to have our equilibriums. So kind of talking through it one more time, we establish our equilibrium. Once we establish our equilibrium, we do need to establish beginning and end from down here. So once we have our beginning and our end, we create a x-axis that's going to sustain that. Then once we create that, let's go ahead and count boxes. I have 6 boxes in between, therefore cut it in half and then cut it in half again to figure out all of our parts. And as you see, I did find what those values are because half of pi over 3 is pi over 6. I would strongly encourage you to find those values. I'm not going to emphasize it quite as much this year, but I strongly emphasize, or I strongly want you to. For this one, if I say, okay, let's set, first let's do the vertical shift, which is down 1. Then if I set what's inside equal to 0, I get x equals 5 pi over 6. If I set what's inside equal to 2 pi, I will get 17 pi over 6. So if I set x minus 5 pi over 6 equal to 2 pi, then I will get x equals 17 pi over 6. Now, that's not a very good thing to be able to put on our graph here, because going from 5 pi over 6 to 17 pi over 6, that is 7. Get 17 pi over 6, not a very nice scale to use, which is why, if you see, I actually set it equal to negative 2 pi, because why not just go backwards instead of forwards if we want to be able to put 5 pi over 6 on the graph in a nice way. So I set it equal to negative 2 pi, which then when we solve, we get x equals negative 7 pi over 6. So that's a lot easier to put on the graph. And now, why even graph backward? Let's actually change that this is now the end and this is now the start, since 0 is after negative 2 pi. So as a negative sine graph, you would have 0, trough, 0, peak, 0. This could be confusing in some ways because there's not really a consistent way that you have to graph every single thing. Yes, we can look at it as a shift right 5 pi over 6, and we can go forward and graph backward, totally up to you. But in between, random train of thought there. So how many spaces in between? I counted, and I sort of jumped over that because I already had the graph there. There are 12 boxes in between, so 6 boxes is halfway. 3 boxes is halfway between those, and that's where I'm going to be creating my troughs and my peaks. Then, if you notice, I'm going to go back to this graph. If you notice, this is the graph of cosine of negative pi over 2, or x minus pi over 2. But if you take a look at the graph, a lot of students said, hey, wait a second, Mr. Beck, isn't that just the graph of sine of x and 2 sine of x? The answer is yes, it is the graph of 2 sine of x. What this shows you is that sine and cosine have a pi over 2 or a 90-degree relationship with each other. And honestly, that's not a coincidence, because this is called the cosine because it is the complementary sign. The reason why we use cosine, it shortens it, but complementary, if you remember, complementary, those sum up to 90 degrees, where supplementary adds up to 180 degrees. But these complementary angles, I mean, really, these are complementary angles to each other. And we're going to experience what that truly means in a little bit, not today, but in the future. So these are off by 90 degrees for a reason. So when we take a look at a graph that's already given to us, we could write it either in terms of sine or in terms of cosine. So if I want to do this, I first need to find my equilibrium, because by finding my equilibrium, I can really see where the sine wave or where the cosine wave will start more efficiently. So if I want to do this as a cosine, this point right here is a very, very key point that I could use if I want to make it a negative cosine graph. This point is what I could use if I want to make it a positive cosine graph. So there's a lot of flexibility for what you want to do with these kind of problems. So if you want to make this a negative cosine graph, which is what we did in class, then we have to find the x value. So this is This is negative pi over 3. Half of that's negative pi over 6. So as a negative cosine value, I'm going to go ahead and have my vertical shift, the negative cosine value. Now, why is it 3? Because our amplitude here is 3. So it's a negative 3 cosine. And what is our horizontal shift? Our horizontal shift is to the left, pi over 6. Pretty straightforward. Then when we get to how do we do this as a sine function? As a sine function, we have to identify where we would need to start, which would be right here because this is the beginning of a positive sine graph. And that is a shift right pi over 3. Now, our vertical shift is the same. Our amplitude is the same, but we wanted this as a positive sine function because of where we're shifting. Could we have done this as a negative sine function working here? And I will say, yeah, sure. We still have the same, so f of x equals, we still have the same vertical shift. I now want this as a negative sine function. The amplitude is still 3. But now our shift is to the right, 4 pi over 3. So this is going to be an equivalent function in terms of sine if we wanted. And we can keep going. For part B, what I'm looking at in part B is, once again, we have to first find our equilibrium. So we officially can find our equilibrium by taking half the peak and the trough. So what is half of 1/2 plus 5.5? That would be 3, which is why both equations you see down here have a 3. Now, just like before, do I want to do this as a positive sign, negative sign, positive cosine, or negative cosine? And because this graph sort of looks similar to the other one, we could choose the same 2 points that we had. So if we start right here, this is going to be a negative cosine. If we start at this x value, this is going to be a positive sign. If we started right here, it's going to be a positive cosine. If we started maybe right here, this is going to be a negative sign. And again, there are lots of different possibilities. Now, if you see, I did do some counting of boxes where this is, if this is pi over 3, and that's 4 boxes, we can make this 4 pi over 12, which means this one right here is 3 pi over 12, which simplifies to the pi over 4 that you see there. So just kind of a little extra practice in scaling. Then our dilation is 5/2, so we can see that because we go up 5.5, we go down 5.5. So then it becomes, do I want a positive sine or cosine? So if I start at this negative pi over 4, that's our horizontal shift. And then because it goes trough, 0, peak, 0, trough, that's why it's a negative cosine. Then if I wanted to start at pi over 4, shift right pi over 4, and that's a positive sine function. Almost there, guys. Next thing that we're going to look at is what happens if we actually finally change the period. Because everything we've done so far didn't change the period. Now we're going to change the period. Now that period, we tend to write this way if we have, oops, try that one more time. So if we have a horizontal dilation, that's what's going to change our period. And the way that you could think about this is in terms of, let's take a look at light waves. Light waves, if you have an ultraviolet wave, you actually have a very, very compressed light wave because it's traveling very fast. If you have an infrared ray, then you're going to have a very long wavelength because the wave's not going to travel nearly as fast, it can travel very slowly. So that horizontal dilation does affect the length of the wave. And because it affects the length of the wave, it affects the period. Now, our period can be found by taking 2 pi over b, which what we are going to eventually do is when we try to find equations, our b is going to be 2 pi divided by our period. So if we algebraically solve that, our b is 2 pi over our period. So we are going to need to know that, or at least have that in the back of our minds looking at these problems. Now, when I take a look at the graph of 3 cosine 2x, we could look at it in a shorthand manner by saying this is a horizontal compression by a factor of 2, which is why when we take a look at our graph, we are now going to compress it by a factor of 2, which is why it goes from 0 to pi. Okay, that's a fast approach to graphing, and I strongly encourage if you see it. Now, if you don't see it, this is going to be the methodical way of graphing these functions. And one more time, we set what's inside equal to 0 because that's our normal beginning. We set what's inside equal to our end. And when we solve that equation, now we go from x equals 0 to x equals pi. So x equals 0 to x equals pi, which that tells me, hey, what is that horizontal distance? That horizontal distance is pi, and then that horizontal distance is always going to be found by dividing by that coefficient. So our 2 pi divided by 2 is just pi. Our beginning is now 0, our end is now pi. If we cut it into 4 equal parts, and let's go ahead and label those on the x-axis. So if we cut it into 4 equal parts, we have pi over 4, pi over 2, 3 pi over 4, and pi. Now this is a positive cosine. As a positive cosine, it goes peak, 0, trough, 0, peak. So really, the difficulty here is, can we put it on a proper scale? And because we're changing the period, we're now going to, say, yeah, how that period changes is going to affect how we're going to put it on the x-axis. So one last thing is this 2. A lot of times we're going to call that 2 the frequency. The frequency is how many occurrences of the wave are between 0 and 2 pi. So if we continue this on out, 2 pi would be right here. What we see is 2 full sine waves from 0 to 2 pi. So that's why it's called the frequency, because it's how many occurrences we have. For this next one, I'm going to go through these in just more of the methodical manner. There are definitely faster approaches to graphing these, and if you see the faster approaches, please use them. I strongly encourage it. 1/3 x equals 0, because what's inside we set it equal to 0. What's inside we set it equal to 2 pi, and we solve. That means we have to put 0 and 2 pi and 6 pi on a common graph, which means let's just go by pi each time. Again, cut it into fourths. So half of 6 pi is 3 pi. Half of 3 pi is 3 pi over 2. And then if we add 3 pi over 2 to 6 pi, we get 9 pi over 2. This is a positive sine graph with a dilation of 4. So 0, peak, 0, trough, 0. I've been skipping over what the actual period is. We could find the period 2 pi over b if we wanted to. In this case, 2 pi divided by 1/3 is 6 pi. We can count from here to here and say that distance is 6 pi as well. So I'm not restricting you to one approach to looking at it. So if we have it algebraically, do it algebraically. If we are seeing the graph, do it graphically. Both ways are going to be important for you to be able to think through. Now notice none of these have a vertical shift on them. I kind of talked through that, but most students are okay with that. Anyway, we have no vertical shift. Now this one's going to be a little bit different because this time we're going to say what's inside that pi x. If we set what's inside that pi x equaling 0 and that pi x equaling 2 pi, what ends up happening is we do get x equals 0, but this time we get x equals 2, which could be kind of confusing because there's no pi. Well, what that means is the scale on the x-axis is actually going to be normal. It's not going to involve pi. So we go from 0 to 2, cut it into 4 equal parts like usual. This is a negative sine graph, so 0, trough, 0, peak, 0. And then we throw everything together. So what's important for us to analyze so that we can see the phase shift is we do need to factor out that b so we understand what the phase shift is. Now that phase shift we can write algebraically as phi divided by w or as h divided by b. Feel free to memorize that if you wish. Not as important to me as I would prefer you to think through it as a dilations, reflections, translations based off of what we did with all functions. So what I can see here, and I'll use that as a frame of reference for is my graph right at the end. So first thing is this is plus 0, so my vertical shift is 0. And then kind of like what I did before, I set what's inside equal to 0 and then solved. I got x equals negative 2 pi over 3. I set what's inside equal to 2 pi and solved. I got x equals 10 pi over 3. So my problem is how do I fit negative 2 pi over 3 and 10 pi over 3 on a common graph? To do that, I'm just going to go by 2 pi over 3. So beginning, end, and then cut it into 4 equal parts. Because there are 6 boxes, I'm going to go 3 boxes and then go 1.5 boxes, 1.5 boxes. That's a positive cosine with an amplitude of 3. So peak 0, trough 0, peak. So a couple of things that we could do at the very end, or actually we could do that at any time in the process. We could say, okay, what's the overall period? 2 pi divided by the b value ends up being 4 pi, and we can check the distance from here to here is indeed 4 pi. I mentioned that we could look at this as what's the phase shift if we factored out the 1/2. By factoring out the 1/2, we get x plus 2 pi over 3. Kind of badly written, but x plus 2 pi over 3. This means that we have our graph shifted left 2 pi over 3. And I like to approach this at the very end just to make sure that what I have on my paper makes sense to me. By going left 2 pi over 3, is that what I did? For a positive cosine graph? Absolutely. For part B, I'm going to start with a vertical shift of 2. From my vertical shift of 2, I'm going to set what's inside equal to 0 and solve, and I get 2 pi over 3. Set what's inside equal to 2 pi, and I get 4 pi over 3. This is a very, very compressed wave. And the reason why it's compressed is because it has a horizontal dilation of 3, so a horizontal compression of 3. So if I put, how do I put 2 pi over 3 and 4 pi over 3 on a common scale? Not very easily, unless I just have to make this a very, very thin graph, which actually kind of makes sense because that horizontal compression. So if I go from 2 pi over 3 to 4 pi over 3, I have 2 boxes. So cut it in half, and then I can create my 0, peak, 0, trough, 0. Just as a quick check, if I factored out 3, this is x minus 2 pi over 3. So that means it's a shift right 2 pi over 3, which is exactly what we did. For part C, we are going to have a vertical shift of 1. So our vertical shift of 1, I set what's inside equal to 0. I set what's inside equal to 2 pi, and I solve, and I get negative 1/2, and I get positive 1/2. So how do I fit this on a graph? Well, let's actually just use the graph wisely and spread it out. So I have 4 boxes in between, so that's easy to cut into fourths. So this is a negative sine graph with a dilation of 2. So it would be 0, trough, 0, peak, 0. And then we can extend the graph like we did before. Quick check. So if we take 2 pi divided by our b value, we get our period of 1. And that makes sense because the distance from negative 1/2 to positive 1/2 is indeed 1. And our last graph kind of puts it all together. Our last graphs put that all together. So very first thing that I want to do, and the easiest one to look at, is what is our equilibrium? Our equilibrium is halfway between the peak and the trough. So I could put that for both my sine and my cosine function. Now, the question is, do I want it as a positive or negative sine or cosine? Which, if we think about how we did that before, I have different representations here based on its location. Now, my amplitude is 4, so it's either going to be 4 sine or 4 cosine. And so for the first one, the last thing that I need to look at is what's my actual period. And this is where I'm going to take, define my b value. 2 pi divided by period gives me b, so the b value is 2. And now what's left is what is the shift and whether it's positive or negative sine or cosine. And I'm going to do this in different color just to say if I want to start here, that means my horizontal shift is pi over 12, which it actually looks like pi over 2 here. It's supposed to be pi over 12. So pi over 12 shifted to the right, pi over 12 to start off with my positive cosine. And then, as I said, positive cosine. If I wanted to start off here at pi over 3, right pi over 3, then that would be a negative sine graph, which is what we see here. And there are lots more possibilities. For part B, we do need to establish what's our vertical shift, or our equilibrium is still going to be at 0. So that's great. You don't have to write the 0 if it's just a 0. Our amplitude is 2.5, which is why you see the 2.5 in front of both the sine and the cosine. If we want this as a cosine, we could do this as a negative cosine because that's right on the axis, so a negative cosine with no shift. If I want to do this as a positive sine, it would be positive sine and x minus 1/2. Now, the b value, once again, if we take our b is 2 pi divided by our period. Well, what's our period? Going from here to here, that distance is 2. So 2 pi divided by 2 is pi, which is why we see the pi out. That was a lot of information to pass on to you. Hopefully this makes sense to you. If you have any questions, you know where to find me.